Yeah. I mean, here's a good teacher, like this. Oh yeah, right now. Something.
Hello, good morning. We have an exam on Friday and there is a homework due on Wednesday. And on Wednesday, we will have a review session like we have had before, basically just go over one of the most probably the previous year. I don't know whether last year I talked about. The latest I have taught, I will go through the midterm 3 of that particular year. It doesn't mean that those exams are more important by any chance. It just gives you a feel for what other questions you have and what are the topics to be covered. And like earlier, the concepts will be concentrating on the homeworks between midterm 2 and midterm 3. Everything stays same. Any questions or comments? Nothing at all. Let me turn the camera up before I forget. We have been slowly switching over from electricity and magnetism to light, and which in the beginning one would think that it's a completely unrelated concept altogether, but it turns out that oscillations or wave-like oscillations in electric and magnetic field is what propagates energy and momentum, and that's what is a phenomena of light. And later on we will make it simple. We'll make simple approximations where the wavelength is small compared to the aperture size, and then we will be able to talk about what is usually studied as reflection and refraction, how light goes through a medium, for a glass, for example, or in a mirror. When you see yourself in a mirror, what characterizes the shape of what you see yourself in? Most of the time it's a flat mirror, but you might have noticed that sometimes when a surface is curved, you look funny inside a mirror. So you would like to see what kind of properties decides those variations in your images. For now, we are slowly switching. We are talking about electromagnetic waves. Let me review the concepts for that. So, electromagnetic waves, light as we see it. When we think of light, we mean the white light that is coming towards us. Sometimes it is, you might have seen a red light, blue light. So those are the forms of electromagnetic waves we talk about when we say it's light, but it is not confined to that. Radio waves belong to the same category. They are examples of electromagnetic waves. X-rays that you might have heard about when you go into a hospital and you have to take an X-ray of your bone or something. That's another electromagnetic wave. And we will see that this is a whole class of waves we have, and it is characterized by what is called frequency, often we call color, and red and blue color, red, green, blue that we see is only a very tiny, very minuscule, tiny window of all the possible colors that is possible in this spectrum. So what is an electromagnetic wave? It is described by very much when it looks on an illustrative diagram like an ocean wave, but the oscillations are not of water, but that of an abstract quantity called electric field and magnetic field, which since we have spent so much time on it, we should have a reasonable feel for it, even though it's still abstract, but a good feel for that. So it is oscillations in electric field in the direction of motion. We'll call this direction of k. It's k hat, means that the vector itself divided by the magnitude. Earlier we drew this as in the z direction, but at this point we don't have to say that is in the z direction, any particular direction in which the wave is moving. So this is direction of propagation. And that is electric field oscillating from a 0 value goes to a maximum value. These are all electric fields, and then comes down. So it oscillates. Notice it is not oscillating at one point. It is of course oscillating at one point also, but here these oscillations are in space. So it's a direction of propagation. If this is at the origin, this is about 1 meter from the origin. So that is a distance. So the horizontal axis here is distance, and this is the direction of electric field. Notice electric field is perpendicular to the direction of propagation. Similarly, there is a direction of magnetic field, which is also perpendicular to the direction of propagation, and it is also perpendicular to the electric field. So these three quantities, electric field, magnetic field, and the direction of propagation, are mutually perpendicular. Electric field, magnetic field, and the direction of propagation k hat are mutually, it's called perpendicular or orthogonal. That's more technical. And let me fill this in. So that's the oscillations in electric field. The magnetic field also oscillate like this. I'll draw that in a minute, but before that, I should point out this is a snapshot of this oscillation. So this is fixed time. So T is fixed. This is how ocean wave will look like if you were to take a picture of the ocean wave. But if you were to release the time, if you take a video of this, that means this point will start moving. So if I think of this as a crest, then it will go down and then come back up. Like that's what is happening in time. So this particular particle, if you were to think of this as an ocean wave, and there is a small water molecule, that's oscillating up and down, but the energy is being propagated. Energy and momentum is propagating in the direction of propagation, which is perpendicular to the actual movement of the molecule. So that's the non-trivial feature of a wave. It happens in an ocean wave also, but here it is the electric field that is oscillating up and down, but the energy and momentum is moving perpendicular to that. Magnetic field is perpendicular to that, but mostly oscillating in the same manner. They are driven, one drives the other, and this is parallel to that, which signifies that these two are perpendicular. Electric and magnetic field are perpendicular, and they are in phase with each other. With phase means that whatever electric and magnetic field does, or electric field does, the magnetic field will do exactly the same thing. And that's because one is driving the other. So they are correlated completely. So that's your So that's the visual representation of an electromagnetic wave. There is a property wavelength immediately that comes out. So that's wavelength. That's the length, how much distance does it take for it to come back to a maximum. And usually this is not easily visible in the electromagnetic waves we see around. But example is microwave is also an example of an electromagnetic wave, and immediately you should ask, what is the wavelength of the microwave that you use for cooking? Most probably all of us have a microwave in the kitchen, and one can ask, what is the wavelength of the microwave that we use? And it's about 6.5 centimeters. And what that means is that if this was oscillating, this oscillation in electric field is what leads to heating up of food. More oscillations mean higher temperature. And this happens pretty quickly. So that is heating of food happening. But what it means is that if you were to keep a plate of pizza here, the points here, because they're having a higher electric field, will be hotter than this point where it is not getting heated up. So if you were to actually not overheat the pizza, if you gradually heat the pizza, you will see that the 2 points on the pizza where they are not heated up uniformly are about 6.5 centimeters about. It is not very easy to see that in an actual microwave because you have this rotating turntable inside the microwave. That is primarily so that this doesn't happen and you get the food uniformly heated. So if you want to really test it, remove that turntable. It's primarily there for making this uniform. Remove it and keep a small object. And if you want to test this, then you will see that this is actually, you can actually measure the speed of light like that. You can measure this wavelength. The frequency is available on the magnetron of the microwave. Behind the microwave, it will tell you what is the frequency it is using. So you have two quantities. You can actually measure the speed of light, or measure means experimentally estimate the speed of light that way, and it will come out to be 3 × 10⁸ meters per second. So anyway, so that's the first property of the electromagnetic waves, that they are perpendicular to each other. I said there is an oscillation in space, that's the wavelength. There is also an oscillation in time. It takes certain amount of time for the electric field to be a maximum, go to a minimum, and then come back to a maximum. That's called the time period of oscillations. And that quantity, T lambda, the distance over time, is equal to the speed of light. So this is, we said it's a whole number. So to 2, so this exactly, it is 792,458 meters per second. Typically, we have been working with 2 or 3 significant digits. That is the best accuracy we can get in a lab setup that we do in our in the labs corresponding to this course. So it is good to say this is about 3.00 into 10⁸8 meters per second. For our purposes, that's the value of speed of light. Often 1/T is also frequency. We talk in terms of frequency. So that's lambda times frequency is speed of light. If this is a constant in vacuum, that means the frequency and the wavelength are not independent of each other. Once you fix your wavelength, frequency is fixed because C is fixed. And that's what I meant when I said that for microwave, this is about 6.5 centimeters. This is fixed. That means the frequency is determined completely. If you know the speed of light, or if you know the frequency, you can actually measure the speed of light. So that's the first property that it is all perpendicular. Second is that wavelength times frequency is the speed of light. And the third is how much is the momentum, right? We said, or let's talk about energy first. Since energy now is spread out, when you think of energy in an ocean, you cannot say energy in 1 centimeter, or energy of the whole ocean has to be divided by a certain volume if you want to talk about energy per unit volume. So we say energy density. That's a easier definition to have than the energy itself. If you had a massive particle, if whenever we are thinking of a car moving, we associate the whole energy with the car itself. But an ocean wave is too spread out, and an electric field in general is spread out all the way to infinity. So the volume is too big and the mass itself is not easy to define that. So the energy density for an electromagnetic wave is equally distributed in the electric and the magnetic part. So that is partially in the electric case and partly in the magnetic scenario. And this is exactly equal to 2 times U of E. Or you can say it is exactly equal to 2 times U of M. And that uses the fact that U of E is exactly equal to U of M. This is good enough, but it is good to notice that the amount of energy that's there in the oscillations of this electric field is exactly the amount of energy that's there in the oscillation of the magnetic field. More explicitly, this is half epsilon naught E squared plus half magnetic field squared over mu naught. That's your magnetic and electric energy. This is energy per unit volume. So we have 3 properties at this point. The electric, magnetic, and direction of propagation are perpendicular to each other. Wavelength and frequency are not independent of each other. If you know wavelength, you know the frequency also, and the speed of light is fixed. Energy density is given in terms of the height of this electric field. Think of ocean wave again. How high does the water oscillate from the mean value decides how much energy it is. But the energy itself is dependent on energy electric field square. But remember that energy is propagating in a direction that is perpendicular to the direction of motion of this particle. And that leads to the idea of momentum. And again, exactly like energy, we talk about momentum density instead of momentum itself. That's given by the letter G. It is epsilon naught times the electric field crossed with the magnetic field. And that turns out to be, if we were to do this substitutions of the fact that electric and magnetic fields are related by speed of light, this comes out to be exactly the energy density of this electromagnetic wave divided by the speed of light, and it propagates in the direction of propagation. So the momentum density and energy density are related by speed of light, which should not be very surprising. Remember, for a massive particle, energy is half mv squared. Right? And so that's energy, and momentum is m times v, right? Mass times velocity is momentum, half mv squared is energy. So if I were to divide this by velocity, that's the connection you have between momentum density and energy density. That's the basic features you need to understand light, or those are the properties that describe light very well. Here we will concentrate in the next part of the lecture just on this piece in here, that the electromagnetic wave is characterized by wavelength and frequency in principle. But once you decide your frequency, the wavelength is fixed because speed of light is fixed. So let me move to the next quote. So this is called the electromagnetic spectrum. Since wavelength times frequency is fixed, C is fixed, we can ask what is the what are the possible wavelengths? Of course, frequency is fixed once you know the wavelength, but you can ask what is the possible wavelength, and the idea is that wavelength can go all the way to infinity. To our knowledge, can go all the way to infinity, and it can go all the way to 0. So every number you can think of between 0 and infinity corresponds to an electromagnetic wave, right? Every number in between. And that means that we can actually put this on a straight line. So let's say this is your wavelength, and that's your 0. Somewhere on this line, there is a tiny window, very tiny window. It's not even visible when you really take it in the, when you break this up. And if I were to open this, if I were to take this tiny piece and zoom it out, on one side, you have the red light, and on this side, you have blue or violet light, right? Let's, violet is slightly bluer than blue itself. That's a violet light. And every wavelength in between is what we associate with the colors of the rainbow, right? So there's a WIP-GR when we say that is violet, blue, red, green, and what is it? Red is the last, right? Green, orange, and orange, yellow, and red. It is good to know what number here between 0 and infinity corresponds to this red light. And this is in meters now. And this is about 680 nanometers. 680 nanometer is about 0.68 micrometer, and 1 micrometer is 1,000 times smaller than a millimeter, right? Millimeter is the smallest division that you can see that typically is shown on a ruler. When you take a ruler, that's about 6 inches. The smallest division of that is a millimeter. Draw 1,000 lines in between them if you can. It's probably not possible physically. Even the pencil tip itself is really thick. But if you can draw 1,000 equidistant lines, that's a micrometer, not even a nanometer. But this is 680 is about 1,000 nanometers. This is approximately 1 micrometer. That's the size of a bacteria. Typically, bacteria is of the size of a micrometer. There are various sizes of bacteria, but typically bacteria are of that size. Here, this is about 380 or 400 nanometers. A smaller wavelength means higher frequency, right? Notice if I have wavelength fixed, so frequency is equal to C over lambda. As this gets smaller, frequency gets larger. And remember, what is frequency? It is the number of times it is oscillating here. More number of times it is oscillating, more is energy. So blue light has more energy than red light. And if you really were to transfer energy from light to something, blue light will have slightly larger energy. It is slightly because 400 and 680 depends on relative quantities. Between these two, this is significantly larger. So blue light is hotter, if you want to say, by more energy. Sometimes we use the word hotter. Blue light is more energetic than red light. There is one point which we haven't studied, which is not very obvious at this point. It will come in as we proceed if in the last week of classes here, is that for some reason the wavelength you use, notice that I have a lot of wavelengths here. The wavelength I used to see something is limited by the wavelength itself. For example, if I use a red light to look at a bacteria, then I cannot see anything smaller than 680 nanometers. If the bacteria is, let's say, bacteria's hand or one of its claws is smaller than 680 nanometers, then you won't be able to resolve that. So the resolution of your viewing of your photograph you take is limited by what light you use. By light, I mean what electromagnetic wave you use. So it is very clear that if you want to see smaller objects, for example, if you want to see virus, you want to go smaller. Virus is significantly smaller than a bacteria, and you cannot use visible light then, because visible light is limited by 400 nanometers. If you want to see an atom is less than a nanometer, you cannot see visible light. That's why you do not see pictures of atoms very well. There are illustrations of what an atom looks like, but you never see atom in motion, right? But if you go to a lab, you will be able to see a bacteria in motion. They will show you in a lab that bacteria is moving around, but you will probably never see a virus moving around, because virus cannot be seen using visible light. What will you use for seeing a virus? First of all, where is the virus? So this is a bacteria, or just for reference. Very broadly speaking, bacteria comes in all sizes. It could be small and big, but they're mostly a micrometer. So this is 10 raised to minus 6 meter. Right? That's a micrometer. So 1000 nanometer is a micrometer. A virus is in this region. That's a virus, and that's about 10 raised to minus 9 meters. That's a nanometer, right? Virus is in the range of a nanometer. Then what is the light you would use? Light, by light I mean which electromagnetic wave you will use. You will start using the range of 10 raised to minus 9, and that is what typically is an X-ray. So an X-ray or an electron microscope. So this is an X-ray. X-ray is a whole range of quantities there. You can also, an atom is very close, by the way. So atom is somewhere here. That's 10 raised to minus 10 meters. That's why virus is so early in the evolution of life, that virus probably is built out of maybe somewhere between 20 to 100 atoms. Maybe I'm off by an order or so, but they have very limited number of atoms. On the other hand, a bacteria is an evolved organism. They have a lot of atoms. Certain atoms do digestive, or certain atoms are used for locomotion and so on, but virus has very limited abilities. In fact, it cannot even sustain on its own. It needs an organism to sustain itself. So it is very minimal features, they're very less atoms. So it is almost in the size of an atom. Atom is 10 raised to minus 10, and put in about 10 or 100 of them together, and you get a virus. So if you want to see a virus, you almost want to see the atom itself, and X-rays are the best objects, or best electromagnetic way for that. What if you go, remember this is energy is in this direction, right? Larger energy is in this direction. So X-rays have more energy. That's why you might have heard that whenever you go to a hospital, when you're taking an X-ray, everyone is taken off the room, and you you do it only for a fraction of a second. If you were to expose yourself to an X-ray for a long period of time, that is not good for your, not good for the atoms inside your body. It can actually break the DNA and so on. So it is not good, but it is high in energy. That's what my point was. What if you go further down? What are the smaller objects? So bacteria, virus, this is an atom, right? That's an atom now. And we're having a reference of what is smaller, like what is smaller than an atom, and that's a nucleus of the atom, correct? That's significantly smaller. And how smaller is that? That's about 10 raised to minus 15 meters. One should appreciate the fact that this is about 10 raised to 5 orders of magnitude. That means to say the atom itself, the electron, is about 1,000,000 times farther than this. It's like saying if you have a 1 meter object and you go 1 million meters away from that, that's the amount of space that is in between. So there's in a way of saying, there is a lot of empty space in between the nucleus and the electron. But that's a small quantity. And then you ask, what is that? There must be an electromagnetic wave of that wavelength. So which means to say that within the diameter of the nucleus, you want to make one oscillation, right? This one, so you should be able to fit one nucleus within this wavelength. So that's the size we are talking about. That's usually called a gamma ray. Too much energy in that. And significantly enough energy that it can hurt you badly. This is what typically happens whenever you think of nuclear bombs and it leading to radioactivity. That's gamma ray, very not at all suitable for us to expose ourselves to. But we cannot help it either, because gamma ray comes from outer space too. Of course, nuclear bombs are a source of gamma ray. In fact, there was an experiment long back which tried to look for gamma rays coming from outer space, and it turned out that most of the gamma rays was coming from the, no, it was opposite. The military placed a lot of gamma ray detectors in the outer space to detect nuclear activity on Earth, but it turned out there was more gamma ray coming from the outer space, and they are called gamma ray bursts, which we did not know about before. But that's just a point I'm trying to make, that gamma rays are there all around us, and from outer space, we do get a significant amount of gamma ray. If you go further down, the smallest distance you can think of as of now is that has been explored experimentally is 10 raised to minus 18 meters. And that's the size of an electron. So this is an electron. As of now, we do not know anything smaller than an electron. For that matter, we do not know the size of the electron either. We do know that electron is smaller than this distance, but we do not know what exactly is its size. Is it 1,000,000 times smaller than 10 raised to minus 18 meter, or is it just 10 raised to minus 18 meters? We do not know that. We just know that that's the smallest distance we have been experimentally been able to explore using high energy experiments. And that's, each one is using an electromagnetic wave. The here point I'm making here is that wavelength decides what electromagnetic wave, and each one can be explored on its own, and it's a field in itself. You can spend your life exploring the properties of this wave. Now let's go to the right hand side of the visible. This is what we are in, right? This is called visible light. We are a tiny speck here, very tiny. That's, our eyes have been evolved only to observe this tiny, very tiny spectrum of the electromagnetic wave, primarily because we evolved ourselves in water, and water is transparent only to this. It's a coincidence, notice that every part of this electromagnetic wave is opaque in water. It cannot penetrate water. But for visible light, it can go through almost 300 meters. And most probably we evolved in water, so we wanted to exploit that. So our eyes exploited that and our eyes used that because we wanted to protect ourselves. So in a sense, it is not very surprising that this is the window we exploit, but that connection is good to make. So that's a micrometer. What about in a millimeter? So that's, I'm going in 10 minus 3 jumps, right? Each time you're making 1,000 times bigger. So this is a micrometer, a size of a bacteria. This is a millimeter. So that's 10 raised to minus 3 meters. That's a millimeter. That's the smallest segment you see on a ruler, right? That's what is basically called a microwave. The particular microwave with a very particular frequency, that's 6.5 centimeters. That means in millimeters, it is 65 millimeters. That's also an example, but then you can have a lot of other, remember every wavelength has an electromagnetic wave associated with it. And some of the times the signal that you use for your internet, sometimes you use satellite dishes for your internet, and that is communicating with another building somewhere in the visible range, and that uses microwave too. So lots of TV signals, when you use your remote, that's in that range, microwave range. And again, broadly speaking, it is in that range. And what else do you, yeah, cell phone also comes in the same. And the idea that this is all actually a millimeter can be highlighted from the fact that you could ask yourself a question that if your food is getting heated up inside a microwave, the reason why it gets heated up is that the water molecule starts oscillating, like you have electric field oscillating here, and a water molecule has a dipole, the charges that are placed a distance away, and electric field oscillations make the water molecules oscillate. So every water molecule in the food can be oscillated using this electric field externally, and oscillating a water molecule is basically heating it up. That's what happens. So then the question you could ask is, if light can get out of the microwave, usually you can see the food inside, right? It is very convenient to see that there is food inside. So light can get out. So this part of the wave can come out. Light can come out. But then why can't the microwave come out of that tube and heat up the water molecules in your body, which is not really good because it really penetrates into the food or in your body, and it can be not good. But what happens is that, so you want to block it. So that's another property which is not obvious at this point. You will see it 2 weeks down, is that like I said, you cannot see things smaller than the wavelength of the electromagnetic wave you're using. Similarly, if you have an aperture, an electromagnetic wave cannot penetrate it if the aperture is smaller than the wavelength. So if I have a microwave that has a wavelength of 6.5 centimeters, if I make a hole in a metal which is smaller than that, it will be difficult for the microwave to go through. That's why you do not get cell phone signals in elevators typically, or any concrete building. Typically, when you go into a government building, you will see that your cell phone signal is weak, and often it leads to a conspiracy idea that, oh, this is government is actually trying to what do you say, hijack your phone or the information in it. It's nothing to do with that. Mostly government buildings are concrete buildings. They have iron rods in between them, and iron rods are placed in such a distance that you cannot have signals going inside that. The government might be, I don't know, they might be listening to you, but probably not, because your cell phone is not working. I don't know whether they really listen to that or not. So that's another way of looking at the point that that's another way of seeing the wavelength of your measurements in there. So that's cell phone, microwave, and all are a millimeter. Remember, a millimeter is the smallest segment you see on a ruler. Go higher, you have 1 meter. Now you're talking about electromagnetic waves which are oscillating, and those oscillations go all the way. 1 meter is almost the stretch of your arms, slightly smaller than the stretch of your arms. That's pretty much a radio wave. Your FM signal, it is common to use a frequency modulated wave inside your cars. They have smaller wavelengths primarily so that they can enter the car. Like car is metallic, and remember, if you have a hole that is the size of wavelength, then it cannot go through. And you can ask, how does an electromagnetic wave enter into your car? That's a metallic object, and you use frequency modulated wave. And these days you use more technology where you mix two waves and so that the carrier signal is smaller than the actual wave. But broadly speaking, you want to use a wave smaller than your car window, right? That's the best way of it. Earlier, if you notice, older cars had an antenna outside the car. There was a small metallic rod that was coming out. Even today, modern cars, there is a small this size length which looks like a tail behind at the car. That's actually the antenna. If you break that, it won't work. So electromagnetic wave itself doesn't go into your car because it's a metallic object. So you need that small protruding object outside so that it can collect the signal for you and get it. Go higher. This is 1 kilometer. This is also used. And a classic example where this is electromagnetic waves of 1 kilometer length. Now that's very long. Is of course you have this amplitude modulated even now you see those radio waves. Some of the radio channels work in AM, and those are kilometer size length. But a more interesting place where you can use electromagnetic wave is one of the technologies that makes a big impact is, at least because there is so much of rivalry in countries not promoting it, but there is a lot of money spent into military, and submarines form a big component of military. And the idea is, how do you communicate with a submarine when it is underneath? And notice I earlier told you that almost everything is opaque. Water is opaque to almost everything you see here. It can hardly go maybe a meter. So that means to say, if you have a gamma ray burst or a nuclear bomb burst, maybe it is safer to go in underneath the water because it cannot penetrate. I haven't researched that, but that's my very naive estimate here, because it is opaque. Except for water, which goes about 100 to 300 meters. And if you keep going, there is a small window around 1 kilometer where the water goes about 50 or 100 meters. So they try to exploit that in military. They try to say that you want to actually communicate with a submarine using a kilometer-sized electromagnetic wave. And now that leads to a bigger challenge that three things I think I have told you, which I have not explained before. One is that if you want to see something of a certain size, you want to use the same wavelength. If you cannot, using a certain wavelength, you cannot see quantities or objects smaller than that wavelength. The second is that if you have an object or a hole in a metallic object, the wavelength larger than that hole cannot penetrate through it. Third is, if you want to detect an electromagnetic signal, for example, you're in a submarine and you are sending something, you want to detect it. And I just now said that you keep a small metallic object behind the car that serves as an antenna if you want. If you want to detect an object, you want to oscillate something of that length. So if you want to detect a 1 kilometer long wavelength wave, you need an antenna that is 1 kilometer long, right? Otherwise, you cannot detect it or at least efficiently detect it. Half of the information will be lost. So if you decide to use a wave that is 1 kilometer wavelength, you need an antenna that is 1 kilometer long, and you are in a submarine, which is not that big. So what do? So then you come up with different ways. One of the ways is to use the whole submarine itself as an antenna. That's the best you can do because that's the biggest size you can have in a submarine. But then you lose information because now that's not 1 kilometer. You do not have 1 kilometer long submarines. And then you have to come up with how can you have information content coming in only when you have only half of the information coming in. So that's very broadly an exposition of what an electromagnetic wave is. We will work with this visible region from next time onwards or starting Monday. And that's what will be called optics. This will be called optics. We will restrict ourselves to visible light and how visible light behaves. Since its wavelength is small, so small, we will be able to approximate things, and we will be able to use geometry to do most of the stuff. As of now, we have been using a lot of algebra, and in the next 2 weeks, we will be able to do most of what we need using geometry of a straight line. That's all. Thank you, and have a good day.
So we can play.
I do not have. If you want, I can available offshore. Typically but after most probably. Sandra? Did you make progress on your research?
Yeah, I'm working on a proposal now.
You have a proposal now. Ah,
I'm working on it.
Oh,
It's
working
not-
on it,
it's
okay.
not finished. I've never done a proposal before, so I have to
yeah,
do it
yeah, of
online.
course, yeah.
And then, so I can either do the research, sign up for, the credit class.
Correct, yeah, you should talk to someone before, okay, so I have made this proposal, but in general it is possible. So just you should decide whether you want to work with Sivakumar. I think that might be the best thing
Yeah,
for you to do. But by any chance, if there is a challenge that someone says, no, that's not possible, he's not available, then I can help you. That's it. You should aim for it. Even that, I will have to go through the department. Everything has to go through the department. If some department says that no, you cannot do this, then you cannot do it.
Is it okay if I keep in touch with you over the summer, because it's gonna be a next semester thing?
Okay, that's possible, yeah.
I don't wanna bother you too much in your relaxation, but.
No, I will be available. It's just that I may not be available in Carbondale all the time.
Oh, I won't be,
So,
I
yeah,
won't be in
If it is on
Carbondale either.
email, that's perfect.
Yeah, it's gonna be email, I'm not saying.
And as you're working on your proposal, keep sharing it also, because what happens is that in such a, if you're putting in so much effort into it, you don't want me or Dr. Sivakumar to tell you that after about 50 hours of your work, oh, this is not what we expected. Like, so you want to share it in between steps after every 5 or 10 hours of work you put in, share it so that you're on the right path. See what I'm saying? There is no such thing as right or wrong. It's just that they are aligned.
Okay.
Dr. Sivakumar might be expecting certain things from you, and you might be going along a different path afterwards.
Right now, I've done the introduction in the background.
Talk to him.
Okay.
Talk to him. Just write an email to him, or if you want, if you feel overwhelmed about it, I can introduce you. He's casual, don't feel overwhelmed at all.
Okay.
I would encourage you to talk to him so that that brings in an alignment for orientation. Is that clear?
Yeah.
And again, don't feel overwhelmed. It's peaceful. Okay?
I mean, I guess I am kind of stressed because this is the first time I've done something like this, but at the
Yeah,
same time, it's.
see, as far as you're thinking about it, that's good. Stress.
Mhm.
Okay. But if you're stressed about the fact that, oh, you might fail, you might not be able to impress Professor Mark, that's a wrong kind of stress. What you want to be stressed about is that how do I do this? And that's a challenge you're taking on. That, if it's a health, I don't know whether it's healthy or not, that's something you want to ask yourself. It leads to stress in the sense that you're trying, it's like solving a puzzle,
Yeah,
right? You try to do it and can you do it? Stress off it.
because for all we know, they just make noises to fight with each other and they don't actually communicate.
Correct, exactly. That is my first criticism I have, is that it seems to be so back in evolution that did they really communicate? And communication is a pretty advanced form of life, but
But at the
that
same,
doesn't mean that you shouldn't investigate. That's
Yeah.
my criticism, or that's my doubt, or.
you know, you would think the same thing for like clownfish and stuff, but clownfish communicate.
Oh, okay, so then.
They're kind of bitches though. They're female, so they're actually matriarchal.
Mhm.
And so the female is gonna be the largest one, and then she has her herd of males around her.
Mhm.
And she'll be like, you go and get this shell so I can lay eggs. And I was like, I don't care if you get eaten by a shark, you go out there and get it.
The society, matriarchal, I mean, when you're a leader, yeah, from our perspective, it looks bad because we are individually.
Patriarchal.
Not only that, actually, I'm not patriarchal, I'm matriarchal, like in my mother's side, my mother is the.
Huh, that's interesting, that's awesome.
Yeah, in my.
Female power.
But it's very confusing because my mother married someone from a patriarch, and so we go by both sides. You know,
Huh.
but, yeah. But it is not only that, I was just saying, there's the fact that you go and give your life to get something for, that's not a human cannot understand that, right? That seems very wrong.
Mhm.
But that's that culture. Right and wrong is very cultural.
So I have 2 clownfish at home, yes, along with the fire.
I'll keep erasing if you don't
Yes.
mind.
And so they are made to pair. Bubbles, the female, she's just mean. She'll nip at baby Nugget, the male, and she'll like force him out of the sea anemone, and she's just mean. It's a weird relationship. It's a lot of domestic violence.
Yeah. Seems like for them to survive, that's what it is, right?
Yeah. But the
There's so much.
interesting thing is that all clownfish start out as males, and then they fight to see who's gonna be the female. And
Yeah, I have heard about this after very briefly. Oh,
they're hermaphrodites.
you were getting recorded, by the way, just for your information.